Hello, calculus friends. It is Friday the 13th, and I am going to do a little calculus. So this is Calculus 2, and we're playing around with Riemann sums. Now, a Riemann sum is a generalization of area. A particular example of a Riemann sum would be using right-hand endpoints, but we don't have to use right-hand endpoints. This problem here asks us to, so we might as well try it. So we have f of x equals 3x cubed on the interval 0, 5. I always find it's a good idea to visualize that first. So a Riemann sum can be interpreted as finding the area under the curve, so that I would want to graph my function, 3x cubed. Oops, where'd you go, function? Yeah, 3x cubed. I'm going to use GeoGebra. And I'm interested in it on the interval from 0 to 5. And so it might help to see that point. And so I'm going to tell the computer, parentheses for a point, I want to see the point 5, comma, f of 5. And that's 375. So I need to adjust my axes. In GeoGebra, we grab the crosshairs tool to move the graphics view. So we can recenter it. Pointing to the axis and clicking allows me to rescale the axis. So I'll be able to see that point. Oh, there it is. Okay, so it's way up there. And then just to draw in that boundary, I'm going to draw the line x equals 5. All right, so I want to find the area in here with the Riemann sum. Now GeoGebra has that lovely rectangle sum function, so I start typing rectangle, and it says, would you like to use the rectangle sum? I say yes, f is my function, tab, starting at 0, tab, ending at 5, number of rectangles. Now they said to use n, so I can't say n for GeoGebra, but I could say, let's do 10 of them. So that means every half a unit, I'll have a new rectangle because I'm going from 0 to 5. And it did ask for right-hand sums. So here, that means the start of rectangle is to the right. So that would be a 1, enter, and it calculates it. So there's an example of a right-hand sum with 10 equally spaced intervals. Let's blow up the font. Let's see, I want options, font size, 24. Let's go even bigger, 28. All right. Okay, so that's the ballpark of stuff I'm looking for. So next thing I need to do is actually calculate it. So this is the last problem in the homework in section 5.2 online. My version gave me f of x equals 3x cubed on the interval from 0 to 5. And I'm supposed to use right endpoints with n subintervals. So first thing I do is to say, all right, each, if it's right-hand endpoints, that means I'm equally spacing these guys. So my delta x is going to be the width of the interval, 5, divided by n. And I'm starting here at 0 and jumping over 5 over n each time. And so that means the places I'll end up will be 1 5 over n over, and then 2 5 over n's over. Hey, Darren. I'm just doing calculus by myself if you want to join me. Cool. Let me turn on the projector. Yeah, so I was playing around with the last problem in section 5.2. You already have? Okay. We'll jump into 5.3 in a sec then. Just want to finish this one since I started it. All right, so that means my x sub i's are going to be 5i over n. So building my sum here, which is a function of n, summing I from 1 to n, the width of each interval, the base of my rectangle is 5 over n. And then I need to plug these x values into my function. My function is 3 times x to the third. And my x values are these 5i over n's. So then I got to clean up that right there. So let's see, cleaning that up, I can pull out the 5 times 3. So for sure I have a 15 over n on the outside. And again, I is the variable here. So everything else is constant. So constant multiples get pulled out. So I have the sum as I goes from 1 to n. And then I'm going to cube these guys. So 5 times 5 is 25 times 5 is 125. I cubed over n cubed. And I can also pull out that 125 and the n cubed. So 15 times 125, whatever that is. We'll figure that out later. And then I'm going to have an n to the 4th out here. And then I'm left with the sum as I goes from 1 to n of the I cubes. And there's a formula in the book for that. So let's take a peek at the book. And blow this up a little bit. Let's see, where's the blow up button? Way down here. Okay, so let's see, that was in section 1, I think. Oh, too far. Maybe it was in section 2. Looks like it was in section 2, yeah. Oh, there it is. Okay, so cubes is this formula over here. Right there. So it's basically the sum of the whole numbers added up but squared. So coming back to my notes here, this is then equal to, we have that 15 times 125 hanging out front over n to the 4th. And then that sum becomes n times n plus 1 over 2, all squared. Now note, if I multiply all of this stuff out here, then I'm going to get n times n, which is n squared. Squared again, I get an n to the 4th. So the leading term in the top is a 1n to the 4th. I have a 1n to the 4th outside. So when I take the limit of this as n goes big, what I'll get is that 15 times 125, whatever that is. And then leading coefficients are 1 over 1. So whatever the product of 15 over 125 should be the area under that curve. And let's check that out. 15 times 125 gives us 1,875, which should be close to what GeoGebra told us. Ooh, that's interesting. Did I make a mistake? That is quite a bit different. Going up to 5. Yeah, so we could ask for more rectangles here, but I don't think that's the issue. I think something else is wrong. Let's go with 100 rectangles. That's not going to change that too much. Yeah, 478. Okay, so I must have a mistake here. Okay, let's see. 3x cubed. Interval width. The interval is 5 wide. Cut into n subintervals. That's okay. Starting at 0, we jump by 5 over n. So that gives us 5i over n for our x values. 5 times 5 is 25, times 5 is 125. That looks all right. And 3 times 5 is 15. Did I write down that formula wrong? No, I got the formula right for the cubes. Oh, I forgot this 2 right here. Okay, so I guess the problem of doing math in one's head is you occasionally miss stuff. So fixing this, if I square this out right here, I'm going to have a leading coefficient of n to the 4th in the top, plus a bunch of stuff. And in the bottom, I'm going to have a 2 squared, which is 4. and I missed that factor of 4. So there's going to be a 4 down there. So my answer is going to be 15 times 125 over 4, which is what, 1875 over 4, which should take me in the ballpark of what GeoGebra had. All right, human error. Divide by 4, and I get 468.75, which is pretty close to what GeoGebra said with 100 rectangles. All right, so good. Going back to the online homework problem, they wanted to know which of these was the right sum. Okay, so they wrote it differently than I did. So I have to match one of these to my work. Let's see. You think it's C? Let's double check. Where's my work here? Okay, so that would be this stage right here. Interesting. That looks quite a bit different. I really got to multiply all that out. Fine. Okay, new page. So the sum of I from 1 to n of I cubed is equal to n times n plus 1, which is n squared plus n over 2. So then we have to square that, which is going to give us what? N squared times n squared is n to the 4th. And then we will get plus an n cubed plus another n cubed, which is 2n cubed. And then n times n is an n squared. And then in the denominator, we'll have a 4. All right, so then we have that 1875 over n to the 4th times that 2n cubed plus n squared over 4. And so cleaning that up, let's see, we basically have to distribute this guy to each term here and divide by 4. So n to the 4th divided by n to the 4th means we'll have 1875 over 4 plus n cubed over n to the 4th will leave us with an n in the bottom. 2 goes into 4 twice, so there'll be a 2n in the bottom and then the 1875 in the top. And then in the last one, we get what, 1875 in the top again. And sorry, this seems like a waste of time. Apologize for signing this homework question. And then what's left, 4n squared in the bottom. And that sounds like what Darren said it was. Yep, C is the correct answer. And check. Good job, Darren. Thank you. And then they actually want us to, what? I know, good job. And then they want us to enter a value for what we found in the limit. And so we had jumped straight to that earlier. And that was 468.7. What does it want? Did I not read it? Okay. Okay, so 1875 over 4. And check. Fantastic. All right. Okay, so that was about the hardest thing in section 2. Yeah. Yep, the limit. Yep, the limits are always the challenging parts. Okay, so let's take a look at some stuff in 3. I didn't see that yet. I'll have to take a look. Okay. Uh-huh. Oh, okay. I wonder if I didn't have your, you were able to get into the live chat once though, weren't you? Yeah, but the second time you couldn't get in. Yeah, and I thought I had invited you. I have to, yes, and I have to do a new invitation. Yeah. So what I was going to try and do, each time I was going to try and post a link to it here. So at the top of Canvas, whenever you log in, the latest Hangout should have a link in there. So if you don't get the invite through Gmail, no, it'll be a different link each time. Yeah, so we'll get new links here each time I do one, if you ever miss a class again. Okay, so. Oh yeah, did you find you had that error? Oh, oh. Because I saw what it was as you did it. Yeah. But I couldn't see it. That's a bummer. Yes. Good job. Yeah. Okay, so let's play around here. So in section 3, we're getting to the idea of the limit of these Riemann sums leads to the idea of an integral. And an integral can always be interpreted as the area between a curve and the x-axis. And so this group of problems in the middle, beginning middle here, is about coming up with the area based on areas we already know. And so without looking in the book, it's going to be hard for you to do any of these problems. So let's see, usually they tell me what problem this is in the book, but I don't see, oh, it's number 17 in the book, I think, yeah. All right, so if we go to the textbook, and this is section 3, some of the problems in this section are based on properties of the integral, which are similar to properties of sums. And then other parts are based on areas that we already know, like the area of a trapezoid, the area of a triangle, the area of a circle or a semicircle. And so number 17 is in this region. So we're trying to find the values of these integrals here based on areas that we know. So the particular one I'm asked about here is 49 minus x squared in the square root. Darren, does that function look familiar to you? Oops. It actually does, and that's an excellent point. So the function is this. Yeah, it looks like it could be simplified, 49 minus x squared. One thing about square roots, although you can break up the square roots on multiplication and say that's the square root of 4 times the square root of 9, you can't do that on addition or subtraction. So this right here is not going to be equal to the square root of 4 plus the square root of 9. So just double check. Order of operations says you should do what's inside here first. 4 plus 9 is 13. So doing the order of operations, we have to find the square root of 13. If we tried to split it, this would be square root of 4 is 2, square root of 9 is 3, square root of 13 is definitely not 5. So it turns out, even though we have perfect squares inside, the subtraction makes them untouchable by the root. So we can't simplify this. My advice on most problems is whip out a graphing utility and take a look at the function there. So I'm going to ask GeoGebra to tell me about that first. All right, and we don't need this or that or that or that. We now have the SQRT of 49 minus x squared, which hopefully will be, oops, I changed my scale. Let's see, how do I return the scale? Settings. I want a scale of 1 to 1. And now I can see, oh, it's a semicircle. Okay. So if I were to write this as y equals the square root of 49 minus x squared and square both sides, I get y squared equals 49 minus x squared. Bringing the x squared over, I get y squared plus x squared equals 49. And so now I can see that this is a circle with a center of 0, 0 and a radius of the square root of 49, or 7. And one cool thing about circles is I know the area of a circle is pi r squared. So this circle has an area of pi times 49. Since I'm only looking at the semicircle, so I want half of that area, so it would be 49 pi over 2 should be the area there. And so we're not asked, oops, where's the problem? So we're not asked to do Riemann sums here. We're not asked to find an antiderivative. We're just asked to, using area formulas we already know, can we come up with this area? And so answer is yes. Once we recognize that function as the top half of a circle, then we can say it's 49 pi over 2. And so that's all that's required on some of these. Recognize the shape as a trapezoid or a semicircle. All right, let's try another one. Graph the integrand and use areas to evaluate the integral. So we need to graph 2 minus absolute value of x, and that is going to be a, actually. Yeah, because the negative in front flips the v, so it's going to be upside down. Okay. And so let's just double check with a graphing utility. Yeah. So let's hide that guy and add a new one. Well, why aren't you hiding? Okay, we'll just delete you. Uh-oh, I broke it. Now let's type something, see what happens. So we want the absolute value of, oh no, we want 2 minus the absolute value, right? 2 minus. Okay, so there's our upside down curve. And I'm just going to draw some lines in here. We only care about this between x equals -1 and x equals 1. And so I just want to zoom in on that region. All right. So we just care about this region right in here. And I can graph that, think about that a couple of different ways. If I also draw the line y equals 1, then I can see I can break up the area. And again, the integral always looks between the x-axis and the curve to find the area. So in this case, I have a 1 by 1 square here. I have another 1 by 1 square here. I have a triangle here that's 1 by 1 and a triangle there that's 1 by 1. And so it looks like these two triangles make a whole square unit, and here's 2 more. So it looks like the area here is 3. Yeah, and so that's all we're asked to do on some of these problems is just graph it. Is there a way to use basic formulas of geometry to come up with the area? Because that's one interpretation of the integral. So let's select A, check. And then it's going to say, all right, what's the area? And we believe the area is 3. Now, just for fun, I'm going to show you another trick in GeoGebra. GeoGebra has an integral command, which will attempt, and I want the third version, which says, what's your function, what x value starting at, what x value you're ending at. And the cool thing I like about this command is it shades it for me too. So I click on it or hit tab to select it. My function here is called what? I can't see it. I think it's called G. Let's try G. Start value is -1, end value is 1. Yeah, it was called G. And so GeoGebra shades that area for me, and it tells me, hey, that area is equal to 3. Which brings up the question, can you use GeoGebra on the test? Answer is for some questions, yes. But we're going to want to see work for others. All right, let us save this and back out. Did I not finish this? Oh, I didn't say check. Okay, fine. Check my answer. Thank you very much. And let's click out of here. And let's try something else. What happens in like 11 to 14? All right, so yes, squared's a bit of a problem. And again, this is one where we need to refer to the book. This is like number 35 in the book. And the instructions on the online homework sometimes aren't as good in the book. So here it says, use the results of equations 1 and 3 earlier in the book. So we got to look back. Oops, am I going the wrong way? I am. Okay, there, okay. So here's formula 3 right here, and let's zoom in on that a little more. Oops, no, that's fine. Where's zoom down here? Let's see. We will do, that line integrals are a whole different idea. And so, no, that's finding the length of a curve is a lot more complicated than the area, it turns out. And we'll get to that at the end of the quarter. So a line technically has no area, it just has length. Yeah. Yeah. Sort of, but you got to throw a few algebraic tricks in there to make it happen. Yeah. So yeah. So that turns out, yeah, finding the length of a curve is way more complicated than area, and we're not going to get to that until like a month from now. We will be doing that. Yeah. 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 It's totally cool, but it's a little tricky, and so we'll get there later. Yeah. So. So again, we're given the formula here. If we have a square that we're finding the area underneath, it turns out we need cubes to find the area. Okay, so that's the formula we have to use here. And the problem here is t squared from 0 to 1/2. So according to the formula, we want to find the integral from 0 to 1/2 of t squared dt. And the book says that you have to take the right-hand endpoint and cube it and divide by 3, and then subtract from that the left-hand endpoint cubed divided by 3. So that's the formula in the book for the area under a basic quadratic function. So 0 cubed is rather nice, that goes away. So I just have to deal with 1/2 cubed, which is 1/8, over 3, which is 1/8 times 1/3, or 1/24. That is the given formula in the book, right here. So we could justify that with Riemann sums, and that was actually a problem from section 2. So just let's do that for fun to review it. So if somebody said to use, say, right-hand endpoints, for the area of y equals x squared from, let's go from 0 to b. Okay, so we'll simplify the problem a little bit. We'll throw a in a minute. So my delta x in this case would be b divided by n equal subintervals. Okay, if I use right-hand endpoints, then my x sub i's are just going to be b times I over n. So my sum as I goes from 1 to n will be the width of each rectangle, b over n, times the function value, which is the x value squared. And my x values look like this, bi over n. Cleaning that up, I'm going to have a b squared times a b, so I can pull out a b cubed. I'm also going to have an n squared times an n, so I can pull out an n cubed. And so all that's going to be left inside is the sum of the I squareds. Now we have a formula for the sum of the I squareds, so my constant b cubed over n cubed is hanging outside, and the sum of the I squareds is n times 2n, no, let's see, n times n plus 1, 2n plus 1, all over 6. That looks all right. And then what we want to do is to get the area, the actual area, we want to take the limit of this as n increases. So here we have to consider that n times 2n is a 2n cubed. So basically what we have here is, this is essentially b cubed times 2n cubed, blah, blah, blah. I don't care about what the other stuff is, all over n cubed times 6. And in the limit here, I have, because again, n is getting big, the leading coefficients, because they have the same power, take over. So that means in the limit, this must be b cubed times 2 over n cubed, oops, sorry, the n cubed is gone, over 6. 2 goes into 6, so that means I get b cubed over 6. So 2, oops, sorry, 2. 3, I can't divide. 2 goes into 6 3 times, there we go. So what that looks like is I'm going from 0 over here to b, and I'm looking at the area underneath a basic parabola. And so what my formula says is from 0 to b, the area is always b cubed over 3. Now check out this is kind of cute. If somebody said, well, suppose there's a number a and it lives over here, what would be the area between 0 and a? Well, wouldn't that just be a cubed over 3? Okay, so somebody else says, okay, well now how would you find the area in between? So just this region right here. Well, wouldn't I take the big area and subtract the red area? Yeah, so the area in between has to be b cubed over 3 minus a cubed over 3, which is the formula the book told us to use when you're working with quadratics. Okay, so we just derived, oops. Yeah, so we just derived this formula that the book gave us earlier, okay? Yeah, and you'll get used to it, because here's the thing, Riemann sums can be a pain in the butt, and for some functions, there is no formula to find the limit, and you're left with just plugging in different numbers for n and hoping you see a pattern. Yeah, so sometimes we're able to continue things this far. For other functions, we can't. Like I mentioned in class the other day, for 1 over x, there's no formula to deal with that. We have to find another way. All right, so let's see. Did we actually do that problem? Hello. Okay, yeah, so we found that was 1/24th, I think, is what I calculated. Answer, well done. Okay, all right, let's see. Let's try a different one. Let's jump to 18, see what that sucker looks like. Okay, so this one says compute the following definite integral as a limit of Riemann sums. All right, so just for fun, I keep using right-hand endpoints. I'm going to use a left-hand endpoint just for the heck of it. So we have 6x plus 1. Now, another note we can make is that is a linear function, so there should be other ways to do it too. So we'll do it 2 different ways for fun. So I have 6x plus 1 from 0 to 6. Okay, so we're asked to use Riemann sums. Yeah, I know, this is like alien notation, right? Something new too. Again, I mentioned right-hand sums are easier, but just for fun, I'm going to use a Riemann with left endpoints, just to show the difference. And it's not too bad for this one. So here I need to note that the length of my interval is 6. So my delta x is going to look like 6 over n. Now here I want to generate left-hand endpoints. My first one will be 0. My second one will be 6 over n. The next endpoint. The next endpoint after that will be another 6 over n over, which would be 12 over n. And the thing I need to realize is for my index I, here I have I equals 1 to get that left endpoint. This one will be I equals 2. This one will be I equals 3. and so on down the line. So we have to offset our i's, because notice here, this is 0 times 6n, this is 1 times 6 over n, this is 2 times 6 over n. So it turns out my x sub i's are going to look like this. They're going to be 6 over n times I minus 1. And just to double check that, when I equals 3, right, I want to multiply that 6 by a 2. 3 minus 1 is 2. So that's what I mentioned before. Usually right-hand endpoints are easier because you don't have to fiddle with stuff as much. That's why I use them, but left endpoints will work just fine. So my sum here, I goes from 1 to n. My width is 6 over n. And then my function says take 6 times your x value, and then add 1. So for the height, and my x values happen to be these red things here. Right, so I have to plug that in here. So I'm going to have a 6 over n times I minus 1. So I got a whole bunch of nested parentheses I need to deal with. So let's see, where shall we start? Why don't we pull out this front 6 over n? So I'll have 6 over n times the sum. And then let's say I have to distribute this 6 over n into the I minus 1. I don't think I have much choice of that. And I have to distribute the 6. So doing this carefully, I have that 6 on the outside. And then I have 6i over n minus 6 over n. And then I have a 6 is just times that. Then we have a plus 1 on the outside. So I've got this part here, and then I have a plus 1 there. This is a 6i over n here, yeah. And it would be in my best interest to distribute the 6 through there. So we have our 6 over n on the outside. Then we have the sum as I goes from 1 to n. So often, and I did this in an example before, like I have a delta x up here, and I have the x sub I, often what I'll do is I'll do what I, oops, that's not a pen. For complicated ones, also I'll calculate what I call the delta A, which is just cleaning up this here before I throw it in the sum. Otherwise, I'm recopying that sum each time, which is a little tedious. So this is one of those cases where I probably should have cleaned that up before I brought it into the sum. Anyway, yes. Yeah, clean it back, clean it up and put it back in, yeah. So that would have been a better strategy here, but oh well, we've already done it. So let's see, I distribute the 6 and I get what, 36 I over n minus 36 over n plus 1. And that is all inside the sum there. So we have properties of sums that if we have the sum of a difference or a sum, we can break those sums down individually, okay? So first, let's just consider this guy right here. So 36 over n is just a constant as far as the sum is concerned, so it just gets carried along. The I is the only thing that's varying. So basically, I need the formula for the sum of the i's here. So for just this part, I have the 6 over n out front times 36 over n, and then the sum of the i's is n times n plus 1 over 2 minus. So now we have to sum up these guys here. Now I still have the 6 over n that's distributing through each piece of this sum here. So I'm going to have my 6 over n. Now 36 over n is just a constant here. So how many times am I adding 36 over n? N times, yeah. So what I have is 36 over n times n when I add all those up. And then finally I can deal with the 1, just this part right here. Yeah, so we're just adding up the 36 over n's, which leads to that right there. Yeah, correct. Yeah, if there's no I, you just have n of whatever you are adding up. Now the same thing is going to happen for the next part. This 1 right here, yeah, if you add up 1 a bunch of times, that's just an n, right? So when I add that on, now remember, we still have the 6 over n hanging around as a multiple of everything. And I have n ones, which is just n. So that's my sum. So notice left-hand endpoints made this a wee bit harder, which is why I say whenever you can, use right-hand endpoints. It usually makes the problem easier. Okay, so now we have to clean up this mess and hope we don't make a mistake. All right, so let's see. This last one's the easiest to clean. 6 over n times n is just a 6, right? The n's divide out. Over here, I get to get rid of one of the n's. And I'm not sure what is 6 times 36. Let's see, that's be 180. Was it 216? Let's double check with the calculator. 6 times 36 is, yeah, 216. Okay. So this middle term is a minus 216 over n. And then over here, I get to cancel a little bit. Let's see, where are my tools? And this is about the last example I have time for. This n cancels with that one. 2 goes into 6 3 times, and that's about it. I will be right out, sorry. So what's left? 3 times 36 is 72, 108. That sound right? So I'm going to have what, a 108 times n plus 1 over n. And then I'd need to take the limit of this as n gets big. Nah, we don't need to multiply that out. All right, n gets huge. Okay, so as n gets huge here, n plus 1 over n, that's just 1. Okay, so I'm going to get a 108 from that part. As n gets huge in the middle here, this whole thing is going to go to 0. The n over n plus 1 went to 1, and 6, well, 6 is always 6 no matter what n does. So I get a 108 plus a 6. And so it looks like the area here is 114. And so there's 2 ways to check this. One, if you were to graph 6x plus 1, you see it's a straight line. From 0 to 2 means we're making a trapezoid. And we would just find the area of the trapezoid, or we whip out something like GeoGebra. So let's real quick, I'm going to graph this from 0 to 6. And let's see, 6 times 6 is 36 plus 1 is 37. And so we're looking at this area right here. So this is a trapezoid with a base on one side of 1 and a base on the other side of 37. And the area of a trapezoid is always the initial base plus the other base over 2 times the width of the interval, or the height of the trapezoid, which is 6. So 38 cut in half is what, 19? What's 19 times 6? Okay. 114, same answer we got with the Riemann sum. So, all right, that's it for today. Have fun with calculus.